And welcome, and I'm Rebecca, and sorry I had to have this at such an inconvenient time, but my schedule this semester is just really packed. So what I wanted to do in this session was to go over a lot of the concepts from chapter 1, because I think, have you had class yet today? Oh wait, but y'all, that's Monday, Wednesday, Friday. Yeah, Monday, Wednesday, Friday. Okay, because I think he's done with what he's going to do with chapter 1. So, if he didn't cover it in class, then I don't think he's planning for it to be on whatever y'all's next test is. And I took a look at your homework, and it was not too terribly hard. So, and I have some problems here that should help with that. So, I have in this worksheet some conceptual questions, as well as some problems to work out, and I'm probably going to skip around because I don't think I have time to do all of them, but I'm going to do the ones that I think are most useful here, and you can ask questions, and then for the others, I'll try to make videos of them so you can watch them on your own time. So these objectives may or may not be correct because I just copied these from a worksheet from a previous year, and so I might not have gotten all of them on here. So identify circuit elements, so be able to see what sorts of things are in a circuit. Identify elements in series and parallel. And actually, let's do that real quick because that's going to be a fundamental concept that is going to be real important to make sure that you have. So let's look at that really quick. Okay, so let's look at this circuit right here where I labeled, I have a voltage source B and then I have a bunch of resistors and I've labeled them. And we want to identify things that are in series and things that are in parallel. And things that are in series, you know they're in series because when a current passes through them, the same current has to pass through both of them. It doesn't have any chance to break off and go in some other direction. That would mean it's in series. Things that are in parallel have to be such that the ends of the two elements have to be touching. So like these ends have to be connected by a conductor, and these ends have to be connected by a conductor with nothing in between. So things that are in parallel and things that are connected by a conductor with nothing in between are always at the same voltage. So things that are in parallel, whatever the voltage change is across this resistor, it has to be the same for both of them because they're in parallel. So even if they're not identical resistors, this one could be 100 kiloohms and this one could be 10 ohms, and it doesn't matter. They have to have the same voltage across them. They would have very different currents, but they would have to have the same voltage because they're in parallel. So looking at this circuit over here, let's see if we can identify anything that's in series. Do you see anything in series? And so what we want to do is we want to look and imagine that we're a happy little current going along. Are there, and I just showed you two things that I go through that if I go through one, I have to go through the other. I don't have a choice. And so that would be, so F and G are in series. And I don't think I have anything else in series because, like, let's say you wanted to say, this is not be correct, if you wanted to say F and C were in series, they would not be, because between F and C, there's a branch, you could go off and go towards E, so those are not in series. Okay, so now things that are in parallel, and we have to be careful because parallel doesn't mean the same thing it does in geometry. A lot of times they look parallel, but they might not actually be parallel. In this circuit, they are. The things that are parallel look parallel, but their ends have to be connected. And so do you see anything that might be in parallel? It's actually going to be A and B, because even though they're not the same type of thing, these are in parallel, because we can see that this end is connected by a conductor, this end is connected by a conductor, there's nothing in between. So A and B are in parallel. And the reason that they are not in parallel with E is because of this resistor C up here. Because between this end right here and this end, there's a resistor in between. And for that same reason, E is not in parallel with G. Okay, now if I took C out, and I just had this, then now in this drawing, oh, they're still not in parallel. Can you tell me why they're still not in parallel? Which was I think that was supposed to be a D. Yeah, it's just my bad handwriting. But yeah. So I would have to take that one out as well for them to be in parallel. Okay, so now they're in parallel. So now we would say that A and B and E are in parallel. I'm just using the abbreviation for parallel there, so I didn't have to write it all the way out. But sometimes you can have things that are tricky looking that are in parallel. Like these two resistors are in parallel because it doesn't really matter what the physical shape is. It is still true that they have the same voltage across them. So like if I look at this end of this resistor and this end of this resistor, they're connected, and this end of that resistor and this end of that resistor, they're connected. So these are in parallel as well. Okay. All right. Determine the number of electrons that provide a certain charge. I never used to do that separately, but I discovered when I was helping people study for their physics classes that a lot of times people they liked having a formula for this, and so I can give you a formula for this. So I can say the total charge equals N times little e, where Q equals total charge, N equals number of electrons, and E equals charge on one electron, which is a constant and is 1.6 times 10 to the negative 19 coulombs. So I think they might, actually I don't think they do. I don't think they give you that formula on your formula sheet for physics class, and I just found that people liked having a formula. So if you know the total charge, now this charge would be, E is officially a positive number, but of course the charge on an electron is negative, so Q would be negative and E would be negative, but it doesn't really affect anything. Define current and use it to explain flow of charge. So our definition of current, I equals dq dt. That's our definition of current. So current is going to be the rate of change of charge. And what does that mean, the rate of change of charge? A charge can't really change. We're really talking about how much charge flows past a point through a point in time. So you're looking at a specific point, what's the charge that goes through that during a specific point in time? So if you just have, you don't have a function to take the derivative of, you could say I is delta Q over delta T. So if I said something like 4 coulombs passes through a given point in a wire over the course of, I'll just write it, so 4 coulombs passes through a point in 10 seconds, what is the current? So that's just going to be 4 coulombs over 10 seconds. And a coulomb per second is an amp. So the unit for current is amp. Are you in physics 2 right now? I mean, the electricity and magnetism physics right now?
Yeah.
Okay. And y'all are probably still doing, like, fields and maybe...
Yes.
Okay, have you gotten to potential yet?
No.
Okay, all right. So you did Coulomb's law with forces, and now you're doing electric fields?
Yes.
Okay. So y'all don't do currents. Y'all will do circuits later in the semester after you've already done a lot of circuits in circuits class. But they do it, they have the slightest little difference in how they do it in physics and how they do it in EE. And EE circuit students either say it was so easy in physics because I already knew it, or they say it messed me completely up because they did it the wrong way. So we'll just have to see when you get there. Okay. Use graphs of charge to identify current and vice versa. We'll look at that. And relate voltage, power, and current. The big thing to relate voltage, power, and current is that power equals current times voltage. P equals IV. Something I didn't put up here that y'all will be doing a lot in Chapter 2 and for the rest of your career is Ohm's law. And Ohm's law is V equals IR. So voltage equals the current times the resistance. And that's super important. Okay, so let's see. That's 12 minutes. I'll do a few more concepts, and I'm gonna pause it, and save the recording. Let's see. Oh, there we go. Okay, so given the current, how do you find the amount of charge that has gone through a point on the circuit during a given time period? So if I just had a constant current, so if it was constant, then constant current, then my charge would equal my current times my time. So that would be like the reverse of the problem I just did a minute ago, where I found the current. I had the charge and the time, and I found the current. This one would be the other way around. But if you have a function, then the charge is going to be the integral from time 1 to time 2 of your current dt. And I have an example of that we'll either do today, or I'll make a video of it. I think you have that in your homework too. How do you find the number of electrons in a given amount of charge? That was the formula that I gave you, that Q equals NE. So that was from the one before. And I don't think I'll do the symbols right now, because that's something you can just look up. I don't think I can, I mostly put them on there if I was, when I have a big group and it's something for people to work on and we can talk about them. But there's nothing for me to explain here. There's just, pictures. You will see slightly different, like for, okay, so for a voltage source, battery or other voltage source, what you're usually going to see in your book is something that looks like that. But you will also see this, where the long line indicates that's the positive side. And you will also see this, which is the same, just this is the positive side and this is the negative side. It's the same thing. You will see all of those, and there's something else that I'm not remembering. There's another symbol that you might see, but all of those would be a voltage source. You will not see current sources in your physics class because current sources don't really exist. They're kind of a theoretical thing. But current source, it's gonna look like this. It'll have an arrow in it that shows the direction of the current. Okay, and then this is a comic called XKCD. It's on the internet, and it's very, very nerdy. And just the other day, this was his comic, and I was like, oh, that's great. I can use that in my circuits class. So just, made up. So you can go through at your own time and see like what these really are. These are made up. And this one, it's slightly different than the picture in your book, but you'd figure it out. So anyway, that's just for fun. All right. Okay. What does the passive sign convention mean about how we label consumers of power? I should have said, I've worded, I don't know, and I've used this worksheet before and I've never noticed this. It should be, I should have said receivers of power and suppliers of power, because receivers and consumers are the same. And here's how we do it in electrical engineering. So let's say I have a circuit and I have a voltage source here and I have a current, and this voltage source I have it labeled as 5 volts and have this current labeled as 2 amps. So I'm going to pay attention to the sign on my element here, and what this tells me is that this side of my voltage source is 5 volts higher than this side. So the fact that it's labeled 5 volts means that the plus side is 5 volts higher than the minus side. This can be very confusing when you see something like this, because you can have this and you will see it. Okay, so this is labeled negative 5 volts. Well, what does that mean? That means this side is negative 5 volts. Okay, let me write it like this. This side, the plus side, is the minus side plus the label. So for example, so the plus side is minus 5 more than the minus side, but minus 5 more really means subtract 5. So like if I had that this side, if was at, I had some reference somewhere, and I had some other stuff going on, and I said this side was at 20 volts, then this side would be at 15 volts. On this one down here, if this side was at 20 volts, what would this side be at?
So wait, you added, you subtracted 20 from 5.
Up here, I added negative 5 to 20 is what I did.
Okay.
Is I added this number to that side.
Okay, so
It would be 25. Yep. And so I think for me, it's easier to think of it that way, is like the plus side is the minus side plus whatever it's labeled. Because whenever it has a negative voltage on there, that kind of just throws me off, because when I look at that, if I said that side was 15 and that side is 20, it's like, well, why is it labeled like that?
Oh, yeah.
Okay, and
Yeah.
and that's why. Okay, so okay, but what this means is, if you remember, I said power equals current times voltage. Well, I look at the sign that the current enters into my element, and I use that sign along with the label up here to get the sign of my power. So this one, the power, is going to be 2 times 5, so 2 amps times a positive 5 volts, which gets me 10 watts. And then if my power is positive, then it is receiving power. If power is negative, it is supplying power. And you would either say, well, let me give one, so this one is easy to say, you're saying it is receiving or consuming 10 watts. Another little hint for you is resistors always consume power. Voltage sources, even though it sounds like, well, wouldn't they be supplying power? Voltage sources can receive power because you can charge them. So like if you have a battery and you're charging it, it's receiving power. So if I had this, situation where I have a 3 amp current, but now it's entering into the negative side of my voltage source, then in this case my power is negative 15 watts and it is supplying power. And you would say it's supplying 15 watts of power. You would not say it's supplying negative 15 watts. You would either give this as your answer, power equals negative 15, or you would say supplying 15 watts of power. You never say it's supplying a negative amount of power. So the negative means it's supplying, but when you're writing it in words, either receiving or supplying, you always use the positive number. Okay, but I want to look at something else. Let's say that I've got so this is my diagram, and I want to know the power received or supplied by my voltage source right here. So I need to look for my current and determine what side my current entered into this voltage source. So if it's going in this direction, so it entered on this side. So it entered on the positive side, so the power is plus 2 times 3, or 6 watts. And you can have negative current as well. So if you have current that's drawn like this, okay, so 3 amps, that's exactly the same as saying negative 3 amps. So these are the same current. So the negative sign means it's the same as if it was going the other direction in the positive sense. But you don't really have to worry about that when you have one of these problems, because you just need to pay attention to, like, if I had this, so if I just look at what as labeled, use everything as labeled, so not changing the signs of anything, this -2 amp current entered into the positive side of my voltage source, and so my power is going to be -2 times +4, or -8 watts, so it's supplying power. Okay, so that was a whole lot on that, just because in previous years I've gotten lots of questions on it. Okay, how much current, relate power to current, we did that. Did we do that? Power, yes, P equals IV. How much current does a 100-watt light bulb in a 120-volt household electrical system draw? So this is, you're not going to get a question this easy on your test. So this is just plugging straight into this. So we have 100 watts equals our current times 120, or I equals 100 divided by 120. And the whole reason I brought this up is because I wanted to recommend something, a strong recommendation for anybody watching this. Okay, so this calculator up here, the version, the computer version I used, says TI-30X Pro, but you only get the 30X Pro in Europe, I think. In the United States, this would be the TI-36X Pro. And you might not see why this is so useful right now, but the reason this is so useful is because this little calculator, which is not a graphing calculator, and so some classes say you can use non-graphing calculators. This one it'll solve the quadratic equation, it'll solve systems of equations, so if you have like 3 variables and 3 unknowns, you just plug them in, it'll do that. And later in this semester, if you've never had to do a whole lot, well, you haven't had to do a whole lot with complex numbers yet compared to what you will have to do. This calculator does complex numbers better than the graphing calculators do. So, and it only costs a little more than $20, and it's fantastic. So, the whole reason I did that problem was so that I could pull up this calculator and then do 100 divided by 120. And get 0.83 amps. So that's the current. What is Ohm's law? Ohm's law is that voltage equals current times resistance, and that's true within a certain temperature range for most objects. You'll use that a lot. And the last one, why should you use some sort of resistive element in every circuit? Well, let's take a look at that. So let's say I had a circuit that was 5 volts, and I don't put a resistor in there. Well, there will be some resistance, but it will be really, really small. And so let's just say the resistance of this wire is 10 to the -5 ohms. Okay, so then if I use Ohm's law, V equals IR, 5 equals I times 10 to the -5, or I equals 5 divided by 10 to the -5. I get 50,000 amps, which is huge. So this is a fire. This is an explosion. So that's why you need to have resistive elements, unless you have a superconductor. Okay, now Let's see, what's the best problem to do? Let me take a look at your homework. Have you looked at your homework yet? Oh, let me stop